number of cameras and then create a real collaborative traffic intelligence. The advanced traffic AI works automatically and detects and tracks all objects in the camera view, including pedestrians up to bicycles. It's a very suitable option for already existing camera network in a city. Traffic Enterprise provides you with full control in all aspects. Everything is processed on dedicated AI city servers, and the system can easily communicate with other parts of your smart city infrastructure. Now we have introduced all products in a nutshell. To summarize it, each product can offer high scalability and its deployment is straightforward. And here is a design of the flow architecture. So there are two products with then lots of slides and words. So now I would like to give my word to my colleague Tom, and he will show you the live demo of Flow.
Great, Lenka. Thank you. Thank you for this wonderful introduction. Let me just to the Flow. I'm already connected over here. This is how it looks. And as you can see on the left side, we have a panel with the basic menu. Here we have the camera view. And on the right side, there is a workspace where we are going to actually set up all the filters. Here we already see in the camera view trajectories which were detected. Different colors actually represents different objects. Here we can disable each trajectory. So if you want to see only pedestrians, here we see only pedestrians. If you want to add bicycles, we can add bicycles very easily, etc., etc. If you notice, each vehicle or each object has some information about it. We can toggle on and off this information over here, just like this. So color, we won't see the color, stationary duration, etc., etc. So we can really set up the view in the way we want to. All right, let's start configuring something. Let's start with something basic, and let's say that we want to know what and how many vehicles went from this bottom direction up to the top. Let's say that that's the city center. So we will create two gates actually, inbound south. We will create one more gate over here, which is going to be the city center gate, and we will create the movement between those two gates just like this. We will rename the movement to from south to city center. And we will select the movement and drag and drop it to the workspace, just like this. As we have it over here, we now see that there were 175 objects going in this direction. But we want to know only motorized vehicles, so we add here a category filter, and we will select light, heavy, bus, and motorcycle as well, cars. All right, and we connect this category filter with the movement, just like this, and we see that there are less motorized vehicles, only 162 matching this filter. Wonderful. That's basically the idea. Let's do something more. Here we have a turning lane. And as we can see, this turning lane is used only in one direction. So we want to have a sensor for wrong way driving. We'll create two gates for that again. One gate we'll name turning lane 1. Another one will be turning lane 2. And we will create a movement in the direction of, we will create and we will create a movement in the direction of the wrong way. Again, we drag and drop it to the workspace. Here we are, get it over here, and we see that there are actually 0 vehicles matching this filter, which is good. Means that no object went wrong way in this turning lane. Awesome. Let's do one more thing. Let's say that we want to know if and when U-turns are happening over here. So we'll create one more gate here, and we will rename the gate to outbound south, and we create a movement between these two gates in the way the U-turn would actually happen. And the movement will be named U-turn, and again we just drag and drop it to the workspace, and we see that there are as well 0 U-turns, which is good, right? Awesome. So we already created 3 sensors here in this one view. All of them were using simple gates and movements. So let's do something more, and let's create a zone. Here we can create a zone just like this, for example. All right, and we can adjust the zone to be exactly in the shape we want it to be. And let's rename it to waiting zone. All right, and we again move it to the workspace. And now we see that there are 226 objects passing this zone in any way. But we don't want that. We want to be informed when there are cars waiting in this zone on the traffic light. So we'll add a category filter. We can actually use here the same one we already used. We'll just connect it with the zone, and now we are filtering only motorized vehicles passing this gate. So that's 205. That's again not exactly what we wanted. We want to be informed about current vehicles there. So we changed the setup of the zone to now. And as we can see, there are actually 0 motorized vehicles right now. Let's see if there is any car coming. Don't see. Maybe we'll see later. Anyway, so now we are actually filtering only motorized vehicles which are currently in that waiting zone. But that's not yet what we want. We want to be informed when there are cars waiting for the traffic light. So we will add one more filter, which is the stationary duration, and we will change the setup to a value of 10 seconds. So we'll say that if there is any vehicle for longer than 10 seconds, show me that. Obviously, for this demonstration, I chose 10 seconds, but in real life, we would use some higher number. And we again connected with the waiting zone. And we see that currently there are no vehicles waiting for more than 10 seconds, which is actually true because there is nothing right now. Let's see if there will come something. Why we do that? So we can now add an action for this filter and change the traffic light, because this filter would actually detect vehicles waiting here on the traffic light. So we can set up a filter to trigger an action and change the traffic light. All right, so we created a few filters. We set those up, and now let's see. Yeah, there is a car actually coming, and we see that there is number 1 as being in the waiting zone, but the 0 because in the stationary duration, because there the car was not waiting there for more than 10 seconds. All right, let's do something more with the data. Let's create some dashboard and widgets. So here on the another tab we have widgets, and we can add these widgets to these filters. So let's use the distribution widget over here, category distribution, apply, and what happens now? Now here in the dashboard we got a widget with the category distribution. We can change it, put it wherever we want to. We can actually change even the settings of the widget and add coloring. So let's say that if there are 0 to 5, it's going to be green. If it's 6 to, I don't know, 15, sorry, 15, it's going to be orange. If it's 16 to, I don't know, 30, 30, it's going to be blue. And if it's 30 and above, it's going to be, let's say, red. Apply the settings, and we see that actually here we got the green. For heavy vehicles, we have 27 buses, which is different, blue and yellow motorcycles, because it's only 8. This way we can adjust it, adjust the coloring any way we want to. But let's add a few more widgets to it. Let's say that we want to know, we want to have a value. For example, to this wrong way and U-turn, we want to have a simple number when wrong way is happening. So we just add wrong ways widget to there, and the same to U-turns. All right, and on the dashboard we got 2 more widgets with a simple number showing us the amount of wrong ways and U-turns on this intersection. All right, let's add one more, which is a statistical value. For that, I will just change this setup to all the time. And let's add the statistical value to stationary duration. Statistics of the waiting zone. So we will see all the statistics of this waiting zone, like here we can see the minimum waiting time, which is obviously 0 seconds, maximum, which is almost a minute. In average it was 38 seconds, and median is 41 or almost 42 seconds. We can again move the widget anywhere we want to. Let's leave it over here for now. And let's add one more trajectory view, which is very beautiful. And I will apply this widget to the category filter, which will show us category trajectories. And apply these settings, and what we got here one more widget actually showing us the view of the camera with those trajectories. Can zoom in and play around, set it in any way we want. In this way, we actually have camera view on the widget with all the statistics, graphs, numbers. We have it all in one screen. All right, great. We created a few widgets, and let's do what we can do now. We need to use the data in some way. We need to process it somehow. For that, we will use here Things, which is another tab over here. It has more or less the same same elements as widgets. But we will just set up the export using these. So let's say that we want to be notified when there is a wrong way or U-turn happening, so about traffic violations. I will use one more operator, and I will connect these two in one, and here I will apply the sync. We'll add value over here, and traffic violations notification object count, and for now. All right, so in this way I actually set the sync to export the data of this wrong way and U-turn in a simple value information anywhere we want. To further set these syncs, we have a documentation available. So if you click here on the help button, you will be actually redirected to our help desk, where we have articles describing the APIs and how to set it up to get the data out of the flow. All right, let's get back in, and actually we covered it all. We created 4 sensors in one camera view, and actually there is no limit in creation. So we could create a zone here in the core of the intersection to see whether there are pedestrians crossing it here in the core, or we could create a zone on this waiting island to count amount of bicycles waiting on the traffic light. Or we really can play around any way we want to. The imagination is our limit, not the software. The software can actually process any amount of filters. So yeah, that's it from this showcase, and I believe it should be questions and answers section now, because I saw some questions to be. What is the ideal use case for the traffic embedded unit? Let's wait until it loads up. So right now I'm already connected to the embedded unit, and here is actually one camera pointing towards the road, and that's actually ideal position or ideal view for the embedded unit. It's not too big but not too small. It's really ideal position. Now let's have a look on what can be achieved on such an environment. So as I was explaining already, on the left side we have the basic menu. Let's hide it for now. Here we have the camera view, and on the right side there is an operating space where we are actually setting up all the filters. Here we see all the detected objects, and those colors represents individual trajectories which were detected. We can turn them on and off just over here. So now we won't see any car trajectories, and so on. And we can really adjust the view according to our needs. We don't want to see the color and the object ID, just to see the classification. So really we can see that there are cars coming. All right. Let's say that we want to know how many and what type of vehicles are actually going through these two lanes. So simply we will just create a gate over here, passing both lanes, and we will drag and drop that gate into a working space. And that's almost done. So we see that there were 1,263 vehicles passing this particular gate. What we can do to better interpret the data, we will apply a widget towards this filter, and let's say we will add the distribution filter. All right, let's leave it like it is. What happens here? We have a widget. A dashboard, and we have a new widget on the dashboard about distribution. So we can really see that there were more than 1,000 cars, 12 buses, more than 200 light vehicles, 17 heavy vehicles, etc., etc. And that's obviously adjusted live according to what is actually happening on the road. So that was the simple counter. But let's see, here we have a vehicle park. There is some small parking space. So, and we want to be informed when and how long cars are parked over here. So what we will do, we will just create a zone over here, just like this. And we have a zone, beautiful zone, great. Let's rename it to parking. And again, we drag and drop it to the workspace. Now, as we see that this zone is pretty close to the pedestrian crossing, so it might happen that that some pedestrian is actually crossing the zone, and we don't want to count pedestrians in that, only cars. So what we have to do, we have to apply one more filter, that's the category filter, and select only the types of vehicles which we want to detect. And now we connect this category filter with the parking zone, and we see that there were like 18 objects detected in the meantime. However, this still doesn't tell us anything about the length of the stay. So it's just that 18 objects were inside of the zone or crossed the zone. So what we have to do, we have actually two options. We can either use stationary duration, which starts counting only when the vehicle or the object is stopped, right? So when the object is stopped, then this stationary duration, as you can see here above, is shown as and is counted. Or second option, what we have is the duration of occurrence, which actually filters all the objects which were in that zone for some amount of time. It doesn't matter whether they stopped or they were moving, but they were in the zone. So for this example, I will use the duration of occurrence, and I will set that I'm interested into objects which are in the zone for more than, I don't know, let's say 60 seconds, so more than a minute. And we will connect it with the parking zone. And we see that out of those 20 detected objects, only 6 of them were in the zone for more than 60 seconds. So we can consider that there were 6 cars parked. If you want to know when and how long, for that we can use a widget. For example, a table widget over here. And this table widget actually gives us information about every single object in that zone. So we see that there were all cars, we see when they came there, when they left, and we see also how long they've been inside. We can actually change the columns, so we don't want to see the license plate or the ID of the object, or we don't want to know the color, and speed is not interesting for us. Apply the settings, and here we have adjusted table. We can obviously export the table into an Excel file and further analyze it, do some kind of filters, graphs, etc. One more thing, what we can use over here, that's the statistical value. And the statistical value will give us another widget to the dashboard, which is the duration of occurrence. I set it for duration of occurrence, and here we see that the minimum was 141 seconds, the maximum is 306 seconds, median is also 306, and average is 284 seconds. So that's the time, how much time objects spent in that zone. That's what we have just set over here. All right. Let's do one more thing. We can see here that there is some congestion happening, that there are many cars actually. So let's create a sensor for that as well. Let's create a zone over here, just like this. All right. And here we have a zone for the one lane where we want to detect congestion or traffic jams. Let me just adjust the zone a little bit so we have it nicer. Okay. Congestion zone, and let's again drag and drop this zone to the workspace. And we see that in total there were almost 600 objects passing this zone. Okay, that's good. I don't assume that there would be some pedestrian or a bicycle, so only motorized vehicles, which is good for us. That's what we want to know. So let's do one more thing, and let's be informed when there are too many cars for too long. So right now we see that there are almost 600 objects in that zone. In total, there were. Let's change the settings to now, and it will show us only the number of vehicles currently being in that zone. So currently we see that there is only one in the zone. There are two more cars approaching, and yes, both of them are in. Okay, so that's one thing, but we don't want to be only informed when there are too many vehicles, but we want to know also how much time they spend in that zone. So again, we will use the duration of occurrence filter, the same one as we used over here. And let's say that we want to filter only cars when there are for longer than let's say 5 seconds. So no, 55. Apply the settings connected with the zone filter, and we see that currently there is a 0 car more than 5 seconds, and it's still 0 because there is no congestion happening right now. Let's give it a second. Maybe there will happen some soon. Anyway, in general, what would happen if here would be some higher number? Then we can really say that there are more cars in that zone and congestions are happening. We can actually apply a widget, a value widget to this filter, and let's add there a color. So if it's above 5, sorry, no, let's say above 4, or yeah, let's say 5. Then make the color red. And what happened here, I created another widget on the dashboard with a simple value, and we see that currently there are 6 vehicles in that zone, 5, and it's red colored because it's above 5. So there are probably congestions happening. Now it's a bit more fluent, so everything is fine. Let's do one more thing, one more beautiful thing on over here, and let's add the trajectory view widget over here to the category. What will happen now? Now we will have this beautiful camera view on the dashboard. Let's just reorder it a little bit so we have it more logically. All right, like this, here, and here. Beautiful. And here we have a nice and beautiful dashboard from this embedded unit, from this one camera. There is only one camera connected to this unit, seeing also the view of the camera, seeing whether there is congestion happening here in this lane, seeing the average time, how much time vehicles spend here on this parking lot. Having also details about the parking and also the distribution of all the vehicles passing these 2 lanes. All right, I think that's probably enough for this showcase of what can be achieved with the embedded unit. Now, word back to you, Lenka.
Okay, great, Thomas. So thanks a lot for this real demonstration. And now let's continue in the presentation a little bit. So here I have one more example scenario for you. So to our customers, we offer a help with the project design phase 2. It means that we can help you to find the best solution for your project. It means how many cameras will be needed, or what type of cameras, or which solution will be better. Should I use the edge devices or the centralized one? And what is actually your use case? What type of data you need from the video analytics? So all of that we can help you to answer, as in this example, where the requirement was to receive real-time classified counts and turning movements. And here we have created a solution only with one panoramic camera and one embedded macro unit, which can actually analyze the whole red area, as you can see. So to summarize all the key points that you should remember about our traffic embedded unit. First, it's a standalone anti-vandal unit with on-edge analytics. It's a plug-and-play device. It means you connect it next to the cameras on a light pole or so and just get the traffic data right away. We'll show you another example and another real scenario now for the AI cameras.
Yes, let me just share my screen with you. All right, hope you can see it now. Now, as Lenka already mentioned, the AI camera has some unfortunately some limitations in processing, even though there are huge advantages in the size compactness and the edge computing. So ideally, the AI camera should be looking in the view of this kind of type, where the actual situation is not too far away from the camera itself to detect all the objects and do all the analysis. Now, for some, yes, okay, the video just got loaded. All right. Let me show you some examples how it can be used in this kind of scenario. So we see that this is a city center somewhere, and let's see whether there are some bicycles passing by. So what we will do, we will create a zone over here. All right, let's just adjust the zone. Okay. And we want to know how many bicycles passed through this zone. So let's just drag and drop the zone over here. Okay. And we see that there were 761 objects, so pedestrians including bicycles. We don't want that, so let's apply the category filter over here to see only, bicycle. And what we have now, if we connect those two filters, we'll see that through from this 672 there were 77 bicycles. We can see all their trajectories over here. So that's great, awesome. But it is not prohibited for bicycles to go through this pedestrian zone. But what is prohibited is to ride on the bicycle. Like this gentleman over here is riding the bicycle, and he should be pushing it through, not riding it. So what we obviously, these riders are much faster than pedestrians. So what we can do, we can apply a speed filter for detecting the fast moving bicycles. And let's add minimum, and now let's just change it to something like this. The speed right now is in kilopixels per hour. So how many pixels in hour the object will pass. But so it is not 100% accurate on the real time, like kilometers per hour. In the next version there will be kilometers per hour, just for you to not to be afraid that there is 200 and 120 and I'm applying it for the pedestrians. Let's just connect it with a category filter, and we see that there were 10 bicycles actually being faster than standard pedestrians. So they most probably were driving through the zone instead of pushing the bicycle. So that is one use case how it can be used over here. And as I can see the view, there is one more thing which I can think of, and here we actually see a supermarket, a window. All right, let's just wait for the picture to load back again. Right. So here is the shopping window, and we want to know how many people were looking on the window. So what we will do, we will create a zone here in front of the window. Again, we will drag and drop it to the workspace. I don't think it's necessary to filter it based on categories, so we can leave it like it is right now. However, what we have to do, we have to filter just the people who were just passing by from the people who were actually looking on the shopping window. For that, we will use again filter of duration of occurrence, where we will say how long the people should be within that zone to be considered like they are really watching on what is inside of the shopping window. So let's say that if there is in that zone someone for more than 10 seconds, we should be informed about it. We connected with the zone. And let's wait for the number to come right up. All right. Yeah, first for the slowdown, that's due to my computer. It has some limitations on computer power, and already doing these filters, sharing my screen and live streaming, that's obviously a lot for it. But anyway, here at the end of the day, it's 51 pedestrians who were in this zone for more than 10 seconds, so we can actually consider them as looking into this shopping window. And obviously these are just filters, and we can apply widgets to those filters to have a beautiful dashboard, as I showed on the for the other video. For example, we can use here the simple value to know when they are happening, or when how many people were actually in that zone. So here we have the value. We can use what else? Let's say statistical value for the speed, which will actually give us this beautiful chart about speed. What was the minimum speed, maximum, average, and median of speed inside of this zone for cyclists, as we wanted to measure, and so on. We really can play around and apply the widgets basically in the same way as I showed on the previous video. And yeah, I think this would be it from the use case. Really important thing to remember is that the view for the traffic camera needs to be much closer to the actual field of interest, where compared with the embedded unit, which has a higher or which can look further away. All right, word back.
And of course, have used the software data for Sky from RCE. Well, let me give a brief introduction. Of course, my name is Tim Adema. Lenka introduced myself already. I'm head of the Department of Roelof's Mobility. Roelof is a company in the Netherlands who would have with 280 employees. So it's not a large, but also not a small company. We are using data from Sky since 2017. We already have 200 locations used by Data for Sky in the Benelux. Benelux stands for Belgium, Netherlands, Luxembourg. You can see the countries here below, so that's our market, and we are partner for using Data for Sky with RCE. Well, in this case, we're going to give an example of the city Leeuwarden. Leeuwarden is a city in the northern of the Netherlands, in the province Friesland. You can see it here in the north. It is a city with more than 100,000 inhabitants, so it's not a small city, but it's mostly common in the Netherlands, city with this kind of number of inhabitants. And in this case, the customer was the city government Leeuwarden itself to have a traffic survey. Well, in this case, it's going to be about the ring, the city ring from Leeuwarden. As you can see, Leeuwarden is a historical city with a city ring built in the 60s, 70s, 80s. But in the red area, this section, it is not provided with a 2x2 lanes, but only one lane in each direction. So the city government wants to make a study in this case, in this area, for having the focus with Data for Sky and also the results for using solutions in this one, because there are a lot of traffic jams and crossing problems in this area. Well, the main objectives was about what is the problem, where does the problem exist, who bottlenecks are going to be, because there are a lot of problems with the traffic flow at the moment. So we provided them by making a complete origin destination matrix with motorized vehicles, but also cyclists, bicycles. The last one is very difficult when you're using traditional ways. So this one was also needed not only for motorized vehicles, but also for cyclists. Well, as follow-up, we had a brainstorm session about possible solutions and simulate the solutions as well, and give, of course, advice about which one is the best option, best solution for providing better traffic flowing, etc. Well, here's a picture about the scope, the area where we did the study, the traffic survey. As you can see at the left, there is a bridge which provided the network with only one lane in each direction. So you can imagine where the traffic jams are going to exist. Directly followed by a roundabout with also one lane and a network section with a crossing with a lot of cyclists, about 10,000 cyclists a day. And the network itself has about 20,000 until 30,000 vehicles per day crossing this section. The whole area covers up about 1 kilometer until this junction where is a traffic light, and the city ring has already 2x2 lanes system. Well, we had 4 areas to make drone images, movies, database for Data for Sky. In this case, we used 8 drones at the same time, 2 hours in the morning and 2 hours in the evening. In the morning from 7 till 9, and in the evening from 16 hours until 18 hours. 8 drones needed because we changed at every 20 minutes the drone because of battery output. Well, here can you see some kind of images which provided drones each junction and section in the network. Well, it was very good weather, but you can see how great the image is going to be, what kind of scope you get with one drone image. it's at least more than 200 meters. Well, you can see here the trajectory. So we merge all the drone videos together like in one database. So output was one trajectory for the whole area, which used for data of sky, for having the right analysis of the complete area, this one. So we had all vehicles collected, all the trajectories, all the cyclists, etc. on each junction in one file. Results are that you can get heat maps with speed, also number of vehicles, etc. In this one, this is an example from the section at the left, sorry, at the right from Leeuwarden, where the traffic lights already there in the 2x2 lanes. You can see for yourself how great the scope is only by one drone. And of course, there was one orange destination matrix set up for the whole trajectory, for the whole area. So we could see on which side, which junction, one vehicle goes to another junction at the same time. Also for cyclists, which is very difficult by traditional ways for following. It was used for simulations in FISM, so we set up six different solutions for this FISM junction in Leeuwarden, and provided with the input-output from data from sky. So it was a better input for FISM to making the right decisions and also the best prognosis. Here you see the traffic jams graphic, where also on behalf of data for sky, we collected it and knew where traffic jams will exceed, etc., or appear in the network for, in this case, the Gebrandiweg in Leeuwarden. Well, my conclusion is that data for sky helped us to get a full orange destination matrix from the whole area, and even so for all cyclists in the area. It's one that's very difficult in traditional way, and we could identify where bottlenecks appear in the network, so to help create solutions that were very effective. In this one, we used the FISM network and calibrate the output from data for sky into FISM, to having the current situation simulated, and so make also the correct prognosis for the solutions in traffic in the traffic network. And of course, at least we had a happy customer with a lot of information to make the right decisions, also political, to have to collect the right arguments for the best solution in this one.
To detect potential conflicts, we use the principle of simulation and prediction of the future state. We use two methods of prediction. The first one is a linear model, a simpler variant that doesn't take into account the rotation of the vehicle's wheels nor the braking. It's used, for example, to predict the vehicle's movements on T intersections or motorways or just straight road sections. The second way to predict the movement of an object in a scene is based on the assumption that the object is in a turning state and it copies a circle. This principle is described by its so-called Ackermann-Stier model. It's more suitable for scenes such as roundabouts or curved roads, and it can eliminate lots of false positive cases which can be identified as potential collision with the use of linear model. It's time to move to the second demo, showing both traffic conflict techniques TTC and also PET. For the second demo, we have here a signalized intersection with little heavier traffic. Let's have a look first on how we can calculate the time to collision. For that, we have a function in the menu analysis where you can set up the parameters for calculating either the time to collision, post-encroachment time, or even heavy braking. So let's start with time to collision. Here you can choose the movement prediction that we're we were talking about earlier in the presentation. So the first one, the linear speed vector, or the second one, the Ackermann-Stier model. So I will choose the speed vector for this intersection. And here you can also restrict the type, so you can calculate the TTC only with respect to cars or to bicycles, motorcycles, etc. So you can restrict even the class of the vehicle. So let's confirm, and the system will automatically calculate all the traffic conflicts. So here we have the list of all calculated conflicts in the scene, and now we can even parameterize each value. So for example, we should set the maximal value for TTC, so for time to collision. So I will choose 1 second to restrict the maximal value, and also the minimal value of TET, which is time exposed time to collision. Basically it means the duration of TTC conflict. And I will set 0.5. That's what we can leave. So you can see that right now we have about more than 160 conflicts, but using these filters or these parameters, I can even I still can select or filter out the conflicts and leave only the positive conflicts. So right now we have ended up with about 30 conflicts in the scene, which are indicated by these arrows, and the arrows are also differentiated by colors. So the red arrows indicates the lowest TTC, and the orange one is the higher TTC, so it means not that serious conflict. The arrows are interactive. It means that you can click on that and actually the conflict will get displayed. I mean, the prediction of that collision will get displayed in the video, and you can even play it. So you can have a look on the whole course of both trajectories and the time to collision, and also these bounding boxes indicates the possible collision if both vehicles would remain their paths at their same rates. So you can see here in this example, the lowest value for time to collision is 0.6 seconds. So in the same way, you can investigate each and every conflict that was calculated in the scene. So you can click on that and you can play it in the video. Another example. Here again, you can go back in the video and play the full scenario, showing the minimal value of TTC and also the collision of the bounding boxes. Now let's have a look on the second example, and that's how to get the post-encroachment time. You will find that in the same menu for safety analysis, but now instead of time to collision, you can select to calculate the post-encroachment time. As we explained earlier, so the PET is actually the time difference between one vehicle is leaving the area of potential conflict and the following vehicle is entering the same area. Again, you can restrict the types, but I will leave all classes marked. And just confirm to calculate all the potential PET conflicts. So here we have the list of conflicts for PET that the system calculated. Again, these arrows are indicating the potential conflict, and it's interactive, so you can click on that and you can investigate it in the video. So let's have a look on some chosen conflicts. So right here you can see the conflict between the vehicle 51 and 22. So you can see, as the definition says, that the leading vehicle 22 is leaving the area of the conflict, which is here, and the car 51 is entering that zone. And the PET is actually below 1 second, so it's 0.72 seconds that this car was already in the spot of vehicle 22. Another example, for example, can be here. So you can see that both vehicles are driving. This one almost 20 kilometers per hour and is going into the direction that this vehicle number 16 was, and the threshold for the PET here is slightly above 1 second. So this is the way how you can visualize and have a look on all the conflicts that was generated by the system. One last thing, what you can do is you can export all of the conflicts into a CSV file so that you can analyze each trajectory and the whole course of the conflict. So that's one option. Or you can also visualize the conflicts in a heat map. So you will choose the heat map overlay and choose the safety analysis, and you can display it either in a heat map or a grid map while choosing the size of the tiles and showing the values of the TTC. So in this way you can actually have a look on the hotspots and on which places there were most of the conflicts and where the TTC value was the lowest.
They have multiple entrances. Schools usually starts at 8 a.m. for all students. This means that most students arrive within approximately 20 minutes before first lessons. And this often makes traffic situation these last 20 minutes upon arrival pretty chaotic. Previously, you would do field studies, you would place several men on site and do observation. This means that you have no documentation and no one has the full overview of the traffic situation. So what we did was that we started using drones combined with data from Sky. And what that made us able to do was that we could count the vehicles, bicycles, cars, and pedestrians. We were able to detect if there were any problematic areas or spots, could be parking areas, kiss and ride areas, etc. We were also able to determine the use of pedestrian crosses, find any near misses, and most importantly, we had very solid documentation for use afterwards. So all of this actually is the basis for suggesting change to improve safety around schools. Right, so this case is a school in a large city in Denmark. And as you can see, this school has multiple entrances. It actually has entrances on all sides. And the municipality wanted an overview of the traffic situation in regards to means of transportation, use of parking lots, which area do parents use to drop off kids, etc. So we made a drone recording for around 25 minutes right before school started. And then we had each object in the recording tracked. And that made it possible to do a visualization like this. Now, these are all the tracks of pedestrians throughout the recording. So each line or track represents one pedestrian in the recording. And this gives you a nice overview of how pedestrians arrive to school. You can tell that this lane down here is fairly often used. And you can also tell that the pedestrian tracks starting here at the cars, they're all students being dropped off by car. And the same goes for this parking lot. And in this area, actually, there's a bus stop. So these tracks are usually students arriving by bus. Now, obviously, you're able to do a count of these tracks. So what I did was I grouped pedestrians and bicycles into the same category, and then I did a count of all the tracks passing these gates. So it becomes very clear that this lane is very often used by both pedestrians and bicycles. And what's also interesting is that if you have a closer look at this parking lot, you can see that the number of vehicles entering and exiting this parking lot is close to the same. And this means that the parking lot is not used for long-term parking, but is rather used to drop off students, as we saw on the slide before. And that actually makes this parking lot interesting in regards to traffic flow and safety. So we had a closer look at it. And here are all the tracks from the recording throughout the video. So red tracks are vehicles, blue tracks are bicycles, and yellow tracks are pedestrians. And what you can see here is that you have quite a lot of conflicts in this area. You have lots of tracks crossing each other, and you have vehicles reversing whilst bicyclists are passing really close by. So this actually does create, I wouldn't say a near miss, but some situation to be aware of. And I just picked this one example of bicyclists passing by here, and then you have vehicles reversing and trying to leave the parking lot. So I'm going to play the video now, and as you can see, the bicycle is actually hesitating and then makes a turn to avoid the car, and then another bicycle is coming. Several cars are reversing. So this means that this area is somewhat problematic in regards to safety. So in general, by using data from sky and drones, you get a really nice overview, and you get very nice documentation of problematic areas, and you're able to make visualizations and video recordings showcasing relevant incidents like this.
Infrared ranging sensors measure the amount of light reflected by an object. These sensors are usually 3 times more expensive than the magnetic ones and also have higher current drain. And the third one here, ultrasonic sensors. Here the emitter dispatches the ultrasound waves instead of light. It's suitable for indoor parking. It's combined with light signals above each parking spot, indicating the current availability. The common disadvantages of all of these sensors are higher demand on installation and also need of drilling into the surface. One sensor has to be placed for each and every spot. Then you have also limited battery life and lower accuracy in case of wrong parking. Except of these sensors, there are camera-based solutions using image processing to monitor current occupancy of each spot. Our own parking detection solution is also one of them. One of the biggest advantage of cameras is large area coverage. It means you can monitor many parking spots using just one camera. Advantages of camera-based parking management solutions. One is that you can use already existing camera network and use it not only for parking management, but also for security and surveillance purposes. Easy maintenance is another plus. Image processing also opens space for various parking violations detection. Some negatives: you will need more cameras for indoor parking. Typically, it's about one camera per 5 parking spots, let's say. Additionally, detection accuracy also depends on the initial setup. So it's important what is the position of the camera, the angle of incidence, resolution, etc., etc. So let's summarize both approaches and compare them in terms of accuracy, detail, cost, and reliability. So entry-exit approach ranks lower accuracy in the long term. That's due to cumulative error that can occur. Area-wide monitoring provides higher level of accuracy from long-term perspective, as you can monitor each spot individually 24/7. Obviously, entry-exit isn't that detailed as the area-wide approach. In and out systems can be much more cost efficient. There are only few entry-exit spots that need to be equipped. Area-wide is more cost demanding, having more components involved. But in terms of reliability, area-wide monitoring gets the credits here again. And what is the focus and mission of our company? That's computer vision. Therefore, our parking management solution is based on cameras and AI brain that makes the parking lot smart. Our parking detection system is using standard IP cameras that are installed on public lights, walls, rooftops, or poles, etc., to detect the occupancy of all parking spots in real time. It cannot only detect whether the spot is free or occupied, but also define the vehicle class, so whether it's car, bus, or motorbike, or heavy vehicle. Then also measure the length of stay or detect several parking violations, for example, wrong or prohibited parking, or that the parking time is over. You can also define spots for electric vehicles and detect whether it's occupied by non-electric car, for example, or create reserved parking spots that are assigned to specific users. Parking detection can be also a combination of both approaches that I was talking about. So it can be in and out monitoring with the license plate detection at the entrances, and then the area-wide monitoring with the vehicle tracking to its final destination. But how does the parking detection solution work? Let's divide the whole workflow into 4 main steps. First step is sensing, which means there is an input sensor. In our case, it's a camera. We use standard IP cameras. There are no special requirements here. The next step is about image processing. There are basically 2 ways. So first is cloud-based or processing on a centralized server. In this case, videos or snapshots are streamed to the cloud or to powerful on-premise server. All communication is encrypted and secured via a VPN connection. The second option is onboard processing. The system recognizes vehicles locally and sends the parking events or detections and images when required. The third step is all about data visualization. Parking detection provides complex web management system where you can immediately see the occupancy status, manage the parking rules, check the parking violations, see the parking history and statistics, see the live view from cameras, and so on. You can also simply pull the data out from the detection system using the Open API. As a last step, there are various options for the data interpretation and presentation, including overview dashboards in a parking detection content management system, integration with some smart city platforms, mobile application for drivers updating the current occupancy, the LED panels at the entrances informing about the free or occupied spots, or even tablet applications for parking guards or even officers reviewing the parking violations. Parking detection can serve as a complex surveillance system where the city can easily see the current occupancy status types of violations. There are nearly 200 parking spaces in this area, and we use only 2 cameras mounted on a building to monitor the whole parking lot, as you can see on this picture. So let's have a look directly into the parking detection web management system to this parking lot. So as you can see here, we are already in a content management system where you can manage the parking lot and see the current view from both cameras. So what you are looking at is the real view from both cameras in Denmark, in Copenhagen. So you can see directly the current occupancy from the cameras. When I go to the overview page, here you have all the important information that you need to know about this parking lot. So the current status, number of free versus occupied spots. So you can see that in total there are 193 spots and 123 of them are free, 70 are occupied. Then you have a list of some parking violations. And also specification of the rules that are applied on this specific parking lot. So there are about 4 rules, like long stay spots, so it's limited by the time. You can stay maximum 6 hours. Then there are some spots dedicated only for buses. Some spots have only short stay, up to 20 minutes. And the last rule about 1 minute parking. You can create as many rules as you want, just easily click and create a new rule. You can select the days of the week that the rule will be valid for, and also select some groups. So let's have a look at the layout and the current status. So here in this menu places you will see the situation on this parking lot and the number of free or occupied spots and number of the violations. So you can see here several icons from this clock or this exclamation mark, and these are indicating some kind of violation here. So for example, here you can see if you click on this spot, you will get detailed information for this particular spot. So it's occupied by a car and it's staying there longer than 5 hours. But for this spot, there is a rule applied that you can stay there maximally 20 minutes. Another violation we can see right here, where there are multiple problems. There are two rules that have been violated. So first of all, it's a spot for buses, but there is a medium-sized vehicle, and also it's only for short stay, 20 minutes. But the car here is parked for longer than 46 minutes. So in this way, you can analyze or have a look at each individual parking spot on this parking lot. Another interesting menu we have here are the statistics. You can create various kind of statistics out of this parking lot. You can select the data range for the statistics, so you can get the data for last 24 hours or 1 week up to last month. You can also restrict the vehicle type, so you can have the statistics for all vehicles from cars up to buses, or you can select only the cars or only the buses. What you can see here is the occupancy history. So we have here from February 3rd up to today. So you can see the changes in the occupancy. Another chart here we have is average changes in occupancy during the day. So you can analyze when most of the cars are going into the parking lot, or when most of the parking operation happen. So we can notice that most of the cars will or goes here between 7 to 9 a.m. during the morning, and then most of them are leaving between 3 to 5 p.m. in the afternoon. You can also export these statistics into Excel files. So this was one example of a real use case, and let's go back to the presentation. As a second example, we have one parking area in Prague in Czech Republic. This is a smaller controlled parking lot with almost 50 spaces and monitored by 2 cameras mounted on light poles. The requirement here was to provide the occupancy data to the city council so that they can control the amount of parking fees collected by a security guard. So here's the real view from both of the cameras, but I will show you again the real situation in our web management system. So again, here you can see the real-time view from both cameras in Prague. As you can see, it's really nice snowy day here. It's really freezing outside. It's below minus 10 degrees. So it's not that usual for Czech Republic. So it's getting also a bit dangerous on the roads, or I believe also on the parking lots. So here you can check the current situation on this particular spot. Again, we have here the same as we had in the case before. So you have an overview page giving you the basic information that you need to know right away about this parking lot. We have here also some parking violations. Or we have here 2 main groups. There are spots that are paid, and also we have created some virtual spots to indicate whether there are some blocking vehicles. It means that if someone is staying there and blocking the way out for other parked vehicles. You can see these parking spots right here. So all of these spaces that are marked here are just to indicate whether someone is blocking the way out. What we have quite interesting here are also the statistics. So again, you can see the average changes in occupancy during the day. What you can see is that most of the cars will park here between 9 to 11, and then most of them are leaving after 3 p.m. in the afternoon once again. But what is really interesting on this specific parking lot is that they are monitoring how much they should collect in parking fees. And you can see here that the strongest day was last Wednesday, February 3rd, and they should have collected more than 18,000 Czech crowns, which is something like 700 euros. 700 euros. And what the city council found out is that they actually have collected on the fees less than they should have, according to the statistics from our system. So thanks to the PD parking detection implementation, the earnings from this parking lot has more than doubled. So far, I have shown you parking lots with marked parking boxes, but our system can also handle situations without defined parking boxes, which is especially a case of on-street parallel parking. Our detection algorithm can measure the length of the vehicle and then also estimate whether the space fits to a bus, car, motorbike, or a small car. This can highly increase the efficiency of parking space usage in the city. So let's have a look at the last example here, on-street parking in the city of Amsterdam in the Netherlands. The goal is to detect the occupancy on this narrow stretch for parallel parking and calculate the length of available parking spaces. Let's have a look on the content management system, and we can see the real view from the camera in Amsterdam and on this very small parking lot. So right now, 2:30 p.m. in the afternoon, there are no cars parked in this stretch. So as I was mentioning, you can have a look on the current the status, and to see actually how many vehicles could fit into this parking area, which has no marked zones or no marked boxes for parking spots. In this overview, we can see that there is also one rule, and that's maximum 15 minutes that the car can stay there. So if any vehicle will stay there longer than 15 minutes, the system or the parking detection system will notify you about that. And you can see that there are about 4 vehicles that could actually fit this parking lot. And the same as for the previous ones, you can again see the statistics and how the situation changed in the history. So have the statistics for last 24 hours up to last 30 days. And again, you can export all of that to create some reports or statistics out of that. Unfortunately, we have no car going by or parking in here, but as I've shown you here, you actually right here, right now there is a car parking, so we can wait for a bit to have a look how the space will change. So we can go to the places, and right here you would be able to see that the space is occupied and it's taken. So yeah, right now you can see that here we have a space occupied, and in the overview we will see that there are actually 2 spaces left that are free, and one is occupied. Alright, that was the last example we had here. So let's go back to the presentation. So I hope that you got the idea, and that also these real examples help to understand our parking detection solution better. And to sum it up, there are a few key features of parking detection system. and why you should actually use it. So, parking detection is a multi-purpose and robust solution that can be used not only for parking management, but also for other purposes like security or surveillance. The installation is faster and simpler in comparison to other technologies, and the maintenance is also easier. Parking detection can utilize existing camera network, and it provides dynamic data in real time, informed